Good day, students. The second lesson in Module 6 is about percent composition of compounds, empirical and molecular formulas. So this percent by composition by mass, this is the percentage by mass of each element in a compound. So to get the mass percent of element, we have the formula mass percent of element equal to the atomic mass of the element times the number of atoms of that element in the chemical formula divided by the molar mass of the compound, and this is multiplied by 100. So how do we determine the percent composition by mass of elements in a compound? First, we find the molar mass of all elements in the compound, and then we find the molar mass of the compound. So in the first step, by the way, we get the molar mass of the elements in the periodic table of elements. Now, if there are subscripts, for example, of each element in the compound other than 1, we multiply the molar mass of the element by the number of subscripts in the compound. Then, to get the molar mass of the compound, we get the sum of the elements of all the elements in that compound. I mean the molar mass of all the elements in that compound. For the last step, we divide the molar mass of each element with the molar mass of the compound, and we multiply each by 100 to get the percent composition of the element. So, for example, carbon is a substance that occurs in two forms, both of which have the same molecular formula, which is C10H14O and molar mass. One type of carbon gives caroacids their characteristic smell. The other is responsible for the smell of spearmint oil. Now we compute the mass percent of each element in carbons. Remember this, C10H14O. And how do we do that? First, we find the molar mass of all elements in that compound. So we have for carbon, you can look this value in the periodic table of elements. Its molar mass is 12.01 grams per mole. For hydrogen, we have 1.01 gram per mole. And for oxygen, we have 16 grams per mole. Now, in the compound, remember the formula is C10H14O. Okay, so we compute first the molar mass of carbon. Again, based on the amount in the or value in the periodic table of elements, we have 12.01 grams per mole, molar mass of each carbon atom. Since we have 10 carbon atoms in the given formula, so we multiply the 12.01 grams per mole by 10, and now we get 120.10 grams per mole. For hydrogen, its atomic mass or molar mass is 1.01 grams per mole. Since we have 14 of hydrogens in the compound, so we multiply that by 14, and we get 14.14 grams per mole. For the oxygen atom, its molar mass is 16 grams per mole. Since you cannot see any number there, that means there's only one oxygen atom in that compound. So we multiply that by 1 and we still get 16 grams per mole. So these are the molar mass of each element in the compound. Now to get the molar mass of the compound, we add the 3 and we get 150.24 grams per mole. So now we get the percent composition of each element by dividing the molar mass of each element with the molar mass of the compound and multiplying that by 100. So we start with carbon. So based on the previous slide, the mass of carbon is 120.1 grams per mole. For hydrogen, we have 14.14, and for oxygen, we have 16. So remember those values. So again, to compute for the percent carbon in the compound, given compound, we have 120.10 grams per mole molar mass divided by the molar mass of the compound, which is 150.24, and we multiply that by 100. Here the grams per mole unit are cancelled, and we get 79.94% carbon in the compound. For hydrogen, the molar mass computed in the previous slide is 14.14 grams per mole divided by the molar mass of the compound, which is 150.24 grams per mole, and we multiply that by 100, we get 9.41%. For oxygen, we have 16 grams per mole divided by the molar mass of the compound, 150.24 grams per mole, times 100, we get 10.65% oxygen. So these are now the percent composition, or the percent carbon, percent hydrogen, and percent oxygen in the compound. Okay, another example. Freon is a trade name for a group of gaseous compounds once used as propellants in aerosol cans, which has a higher percentage of chlorine. Is it Freon 12 or Freon 141B? So, to compute which has higher percentage of chlorine, first we compute the molar masses of each element in the two compounds, and then we get the molar masses of the compound before we compute the percentage of chlorine for each of the two compounds. So we start with finding the molar mass of all elements of that compound. So again, carbon has molar mass of 12.01 grams per mole, hydrogen has 1.01 grams per mole, chlorine has 35.45 grams per mole, fluorine has 19 grams per mole molar mass. So those are the molar masses of the elements in the compound. But we have to multiply these first with the number of these elements in the compound, no? Or we multiply them by their subscripts in the compound. So we find the molar mass of the compound for Freon 12. Again, this is the carbon molar mass, 12.01 grams per mole. In the Freon 12, there is only one carbon atom, so we multiply that by 1. And we have 12.01 grams per mole for carbon in Freon 12. For chlorine, its molar mass is 35.45 grams per mole. We have 2 chlorine atoms here, so we multiply that by 2, and we get 70.9 grams per mole. For fluorine, its molar mass is 19 grams per mole. Since we have 2 fluorine atoms, we multiply that by 2, and we get 38 grams per mole. And the molar mass of that compound for Freon 12, we will add these 3 values, and we get 120.91 grams per mole. So this is the molar mass of Freon 12. Remember this value for chlorine, 70.90 grams per mole in Freon 12. For Freon 141B, we start with carbon, 12.01 grams per mole. Since there are 2 carbon atoms, we multiply that by 2, and we get 24.02 grams per mole. For chlorine, we have 35.45 grams per mole. Since we have 2 chlorine atoms, so we multiply that by 2, and we get 70.9 grams per mole. For fluorine, we only have 1 fluorine atom here, so we multiply 19 grams per mole by 1, and we get the same value. Then for hydrogen, we have 3 hydrogen atoms, so we multiply 1.01 grams per mole by 3, and we get 3.03 grams per mole. So to get the molar mass of Freon 141B, we get the sum of these 4 values, and we get 116.95 grams per mole. Okay. The molar mass of chlorine in this Freon 141B is 70.9. So now we get the percent chlorine for each for Freon 141B and for Freon 12. So how much percent chlorine in freon 12? How do we do this? We divide the molar mass of chlorine in freon 12 by the molar mass of freon 12. So as computed in the previous slide, we have 70.90 grams per mole chlorine in freon 12 divided by the molar mass of freon 12, which is 120.91 grams per mole, times 100, we get 58.64%. For the percent chlorine in freon 141B, the molar mass of chlorine as computed in the previous slide is 70.90 grams per mole divided by the molar mass of the compound, which is 116.95 grams per mole. And we multiply this by 100, we get 60.62%. So therefore, it's freon 141B which has the higher percentage of chlorine, which is 60.62%. Empirical formula. When you say empirical formula, this is the lowest possible whole number subscript to represent compound, ratio, and types of elements. Like for example, for benzene, its chemical formula is C6H6. And look at these numbers. These are divisible by 6. So this can be reduced to CH. No? Its lowest possible whole number would be 1 for the carbon and hydrogen. Acetylene, on the other hand, has the chemical formula of C2H2. Since both subscripts are divisible by 2, so it can be reduced to empirical formula of CH. Okay, so that's empirical formula. It's the formula with a whole number with the lowest possible whole number subscript. How do we determine empirical formulas? First, we convert grams of each element to moles. So if you are given grams, you have to convert that to moles. Then divide the answer. So the moles we have computed in step 1 will be divided by the smallest value. And then we round off to the nearest whole number if and only if the number has 0.9. If you have our number here 0.9, then that could be plus 1. So for example, if we have 2.9, we can round off that to 3. And if we have 0.0, then we can round that off to the same number. Like for instance, if we have 2.0, then that's equivalent to 2. If step 3 is not applicable, then we select a multiplier which is common for all that will result in the smallest whole number ratio for the value. So that will be identified later on once we solve the problem. For the last step, we assign the answers in steps 3 or 4 as the subscript for each element. So the numbers we computed in steps 3 and 4 will be the subscript of the element in the compound. Molecular formula. How do we determine, or what is a molecular formula? It has the exact number and types of elements. Empirical formula has the lowest possible subscript, whereas in molecular formula, it has the exact number and types of elements. So in determining the molecular formula, we need to have the empirical formula first. Obtain the empirical formula mass based on the empirical formula, and then we divide the molecular mass, which is given. So this value is given. We divide that by the value obtained in step 1. And we multiply each of the subscripts in the empirical formula by the answer in step 2. So let's have an example. A compound used as an additive for gasoline to help prevent engine knock shows the following percent composition. We have 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen. The molar mass is known to be 98.96 grams per mole. Determine the empirical formula and the molecular formula for this compound. So in this problem, we have to get the empirical formula first. Again, the first step is we convert mass of each element to moles. In the problem, we are given with percent composition of the element in the compound. So here we will assume 100 gram mass of compound, which means to say that the number which appear in the percent composition of the element is still the number we put in the mass of the element in the compound. So if you have 71.65%, that's 71.65 grams, no, mass, because we assume 100 grams mass of the compound. So what we do, we will convert that mass to mole. So in converting mass to mole, again, we use the molar mass of the element. So we refer to the periodic table of elements for the molar mass of chlorine, which is 35.45 grams. So in this case, since we're going to convert mass to mole, we have to put the mass in the denominator, so as we can cancel it, no? We can cancel that unit, and then we put the mole in the numerator. So 71.65 divided by 35.45 is 2.02. For carbon, the given percentage is 24.27%. So to convert that to mass, that's still the same value, 24.27 grams, because we are assuming again 100 grams mass of a compound. So to convert this mass to mole, we use the molar mass of carbon we find in the periodic table of elements, and that value is 12.01 grams. Again, we put that mass in the denominator so that we can cancel that unit, and then we put the mole in the numerator. So that mass unit is cancelled. 24.27 divided by 12.01 is 2.02 moles. For hydrogen, the given percentage composition is 4.07. So its value in mass is 4.07 grams. Then we multiply that by the molar mass of hydrogen, again putting the mass unit in the denominator. Then we put the mole in the numerator. We can cancel out the mass in grams. And divide 4.07 by 1.01. We get 4.03 moles. Okay, so now we have converted the mass of each element to moles. The next step is we divide the answers in step 1A by the smallest value. Recall that we have converted hydrogen, carbon, oxygen to mole. So we will compare which of the three has the smallest value of mole. Okay, based on our computation, chlorine and which one? Carbon has the smallest value. So we will use 2.02 because it is the smallest value we have computed, no, for the mole. So we divide mole of each element by the smallest value, which is 2.02. So for chlorine, the mole chlorine we have computed is 2.02 divided by 2.02, we get 1. For carbon, the mole carbon we computed is 2.02 divided by the smallest value, which is 2.02, so we get 1. For hydrogen, the mole hydrogen we computed is 4.03 mole divided by 2.02, we get 2. Okay, so these are now the what do we do with those values? We assign these values as subscripts to each of the elements. So for chlorine we have 1, for carbon we have 1, and for hydrogen we have 2. So therefore the empirical formula is CH2Cl. Again, the subscripts are what we have computed in the previous slide. Okay, so that is now the empirical formula. Next step is we determine the molecular formula. We do this first by obtaining the empirical formula mass based on the empirical formula in the previous slide. So here we have CH2Cl as our empirical formula. To get that mass, we use the molar mass of each of the elements present in that compound. So we have 12.01 grams per mole. This value again can be obtained from the periodic table of elements. Since we only have one carbon atom, so we multiply that by 1. For chlorine, its molar mass is 35.45 grams per mole. We only have one chlorine atom here, so we multiply that by 1. And for hydrogen, its molar mass as found in the periodic table of elements is 1.01 gram per mole. We multiply that by 2, since we have 2 hydrogen atoms in the empirical formula. So that becomes 2.02 grams per mole. So the empirical formula mass therefore is, so we get the sum of the three values, we have 49.48 grams per mole. Next step is we divide the molecular mass, which is actually given by the value obtained in step 2a. So this mass, this mm is given in the problem, which is 98.96. The empirical formula mass is what we have computed in the previous slide. So 98.96, again, this is given in the problem, divided by the empirical formula mass, which is 49.48, we get 2. Now what do we do with this number? We will multiply this with the subscripts in the empirical formula of the compound. So again, the empirical formula is CH2Cl. No, this should not be here. The empirical formula is CH2Cl. We multiply that with the number in the previous slide. We multiply that number with to the subscripts of each of the element in the compound. So that becomes 2 times 1 we have 2, 2 times 2 we have 4, and 2 times 1 we have 2. And this is now the molecular formula of the compound, C2H4Cl2. Okay, so now we have the molecular formula and the empirical formula of the compound. Another example, benzoyl peroxide, an ingredient of some topical acne products, contains 69.42% carbon, 4.16% hydrogen, and 26.42% oxygen. Its molar mass is 242.24 grams per mole. Determine the empirical and the molecular mass of the compound, formulas of the compound. So again, we determine first the empirical formula by first converting the mass of each element to mole. So we are still given percent composition of the element in the compound. So again, that value is still what we use as the mass of the elements. So for carbon, we have 69.42 grams times the molar mass of the carbon is 12.01 grams. So we put that in the denominator and we put the mole in the numerator to get 5.78 moles. For hydrogen, to get the number of mole, we have 4.16 grams times its molar mass. So 1 mole per 1.01 gram. Then we have 4.12 moles. For oxygen, we have 26.42 grams times 1 mole per 16 grams. So we cancel the mass unit and we get 1.65 moles. Okay, the next step is we divide the answers by the smallest value. So the smallest value of mole we have computed, that should be in the denominator. Okay, for carbon, the computed mole is 5.78 divided by the smallest value is 1.65, so we get 3.5. For hydrogen, we have 4.12 moles divided by 1.65 moles, so we get 2.49 or 2.5. For oxygen, we have 1.65 divided by 1.65, so we get 1. Now, we cannot round off these values to, because this is 0.5, no? So we have to multiply this by a number so as we get whole values or whole number. So we can multiply these by 2 and we get 7 for carbon, and for hydrogen we get 5, no? So these are now the smallest whole number ratios. So again, we multiply all. So even though for oxygen it's already whole number, we still have to multiply that by 2, since we multiply the other elements by 2. So these are now the subscripts for our empirical formula. So we have C7H5O2. And to get the molecular formula, so we first obtain the empirical formula mass based on the empirical formula. So we have 12. 0.01 grams per mole as our molar mass for carbon, since we have 7 carbon atoms. So we multiply this by 7 and we get 84.07 grams per mole. For oxygen, we have 16 grams per mole times 2, we have 32. And for hydrogen, we have 1.01 times 5. So we have 5.05 grams per mole. And the empirical formula mass then is 121.12 grams per mole. Okay, next is we divide the given molecular mass in the problem by the value obtained in the previous slide. By the empirical formula mass. So, we have 242.24 grams per mole. This value again is given in the problem. Divided by 121.12 grams per mole, which is the empirical formula mass computed in the previous slide. Then we get 2. So this number now is what we multiply to the subscripts in our empirical formula. Cancel this. So we have C7H5O2 times 2. So C7 becomes C14, H5 becomes H10, and O becomes O4. And this is now our molecular formula. Okay, C14, H10, O4.